So what happens is, as a star is born out of nebula, so we need a cold molecular gas cloud to actually make the star, then it becomes a T-Tauri star, and then well goes prototar, T-Tauri star, and then its regular fusion process puts it on this main sequence strip where it spends 90% of its lifetime. So a star like our sun spends 90% of its life here. Now that number is not, the lifetime of the star is going to depend upon where on this main sequence strip it is. So these redder, smaller stars to the right, they're redder because they're a lower temperature star as classified in this M category. So they're on the lower right. So they can last like literally billions and billions and billions of years because they could constantly mix their fuel. They're constantly fusing hydrogen into helium, and they could do that for a long time. And it just has a really well mixing process when it's a small mass star. Now, medium-sized stars are right here in the middle in the main sequence, like our sun. And these are medium-sized stars. So our sun is lifetime is a span of about 10 billion years. So we're about halfway through that. Okay, so other stars like our sun will have that same predicted lifetime. And we go through the hydrogen fusion in the core that takes the hydrogen, makes it into helium, and produces energy in the process. And when that starts to, when we start running out of the hydrogen fuse to form this helium, then it starts burning these shells of helium, and it starts bloating. And so as the sun progresses through its lifetime and runs out of fuel, it will jump into this giant category and be a red giant. And then when it's done with that stage, it will become a white dwarf. As a medium-sized star, that's its evolutionary chain. So then moving up towards the upper left of this HR diagram, we have the hotter type stars. We're looking at the B and O spectral types. We're talking about 10,000s of degrees as far as the surface temperature goes in Kelvin. So these stars right here will have shorter lifetimes. They burn through their fuel much more quicker. Okay, so their nuclear reactions, because they have so much more mass, it's crushed together in the core, and it just creates these really fast chain reactions. Okay, so these we'll talk about the ending of their lifetime, which typically is a supernova and leaves a neutron star core behind. So depending upon whether you're in the middle or here on the bottom right or on the top left, will predict how the rest of your life will live out as a star, how you will end as a star. Okay, so really important ideas here. So we talked about how these are, the spectral types are associated with the temperature, and then up here on the vertical axis is the luminosity. And we know luminosity increases with temperature and the size. Okay. So one other thing to point out here too, a lot of these classes that are grouped together, like medium-sized stars like the sun, all have the same density. And the same can be said with these red dwarf stars here. They have the similar density. And same with these high mass blue stars. Okay, so, okay, we also have these subcategories. In the G classification, like the sun is a G25 star. The 5, Roman numeral 5, stands for main sequence. The G2 means it's hotter than a G1, but it's cooler than a G3 stars. So we have these we have these numbers to do these subcategories of the spectral types to help give us more of an indication of the temperature differences. And there's the, for main sequence stars, we have that mass luminosity relationship that tells us, you know, how much more mass of the sun, if we increase the stellar mass of a certain star, how much more luminous it will be. So moving on. So here's some of the principles that we want to look at when we're going to address how stars evolve and live out their life. So some of these terms to be familiar with that come up a lot are hydrostatic equilibrium, nuclear fusion. In particular, for nuclear fusion, there's something called the proton-proton chain, and then there's also something called the CNO cycle. And we'll look at the differences in these based on the mass of the star. And some other principles that come into play are conservation of mass and energy. I combine them. You know, you might see them separate in your textbook, but mass and energy are really equivalent. That comes to the E equals mc squared equation, right? Mass is the same form as energy. Mass is nothing but frozen energy. So I'll get to that in the next slide. And this principle of conservation of charge and conservation of angular momentum, which we talked about when we were looking at the solar nebula theory. It talks about all the spin relationships in orbital mechanics. Okay, so here, these principles, visiting it a little bit more in depth here. Conservation of energy. So this is this principle that says the amount of the energy in the universe is constant. And this is going to have some big implications when we look at the beginning of the universe in cosmology, like the Big Bang. All the energy at the beginning of the universe is still the same today. Okay, so some of that energy is frozen, has become frozen into the mass form. Okay, but energy cannot be created nor destroyed. That's an alternative way of saying it. But the amount of energy is constant. So, you know, you could cook something on your stove and you could say, here's a little isolated system. The amount of energy as I start cooking is going to be the same as the amount of energy after I cook. So the energy, the value in joules, which is our standard measure for energy, is going to be the same before and after a process. Okay, sometimes it might seem that some of that energy disappears. You know, we have different forms of energy, like mechanical energy, heat energy, chemical energy. So there's a lot of forms of energy, but it's, if you add up all the energy pieces before a process and after, it's always the same. Now, since mass is nothing but a form of, excuse me? Was there a comment? Somebody have a question? All right, yeah. Let me know if you do. You could stop. It's okay to intervene. That's definitely encouraged, especially when we're learning all this material. Conservation of mass is the same thing. So mass is nothing but frozen energy. And the idea is the amount of mass you have before a process will be the same as afterwards. Now, sometimes it looks like mass disappears. Well, it disappears in the form of energy. And this is what happens with nuclear processes, right? When we take, like for the sun, when we take hydrogen atoms, we slam them together to form helium atoms. The helium atoms are a lower mass than the initial hydrogen atoms. So the question that comes up is, what happens to that remaining mass? Well, it's turned into energy, the energy that lights up the sun and creates the energy that is emitted from the sun. Okay, so again, the amount of mass in the universe is always constant, and it's a form of energy. Conservation of charge is also the same thing. Now, we don't talk about that as much, but that comes into play when you're looking at different types of stars that have a lot of charge values involved, like white dwarfs. Okay, so charge is the positive and negative values. So charges, we know that like charges repel each other and unlike charges attract. And so when we have like a negatively charged, let's say atom, and we have a positively charged atom, we could combine them because the negative and positive will attract one another. Now, positive charges repel, like two protons will repel each other and two electrons will repel each other. But if we were like, let's say we were on, like on a dry day when you have a lot of static electricity, and let's say you've run things in the dryer and all these blankets are rubbing against each other, right? There's a lot of friction, there's a lot of exchange of charges, and you'll feel all those electrons. Now, you might pull those blankets out of the dryer and you might feel some of those charges, the little electric shocks from those charges jumping onto you from the blankets. Okay, so the amount of charge in that system is the same. So there's a lot of electrons there. They're just moving around a lot. They're moving from one surface to another. So, but the amount of electrons in that system will always be constant. And the other main principle that comes into play that we talked about is the conservation of angular momentum. And angular momentum is nothing but the rotational mass, which we call moment of inertia, times the angular velocity. So if you change one of those aspects, the other one has to compensate. So again, this is like that ice skater, right? So as an ice skater wants to increase their speed, they'll pull their arms inward towards their axis of rotation. That makes them spin faster round and round. Now, the same thing happens with stars as with planetary systems. So we'll see what happens with stars when a star's core begins to collapse, right? When you start bringing all that mass inwards and you're shrinking the radius, right? So you're making that ball of a star smaller, you're shrinking the radius, it starts to collapse. It begins to spin faster and faster. And that's how we get like these stars called neutron stars spinning rapidly into what we call pulsars, which are a type of neutron stars. They spin so fast because the mass is pulled inward. Okay, and that's by the principle of conservation of angular momentum. Now, if we pulled it outward, it would spin slower. So you could go either way. So very important principle when it comes to just about everything in astronomy. Okay, so now this principle of hydrostatic equilibrium comes into play a lot, especially when we talk about star stability. So, you know, stars are stable when they're in the main sequence stage of their lifetime. And they're stable because what's happening is they are burning this nuclear fuel in the center, and the radiation energy, the light energy, or you could think of it as the photon pressure. The pressure is acting on there's several layers here. So it acts layer by layer, but that light is pushing upwards, outwards from the star. Now, gravity acts on anything with mass. The more mass you have, the more gravity it's going to act on you. So gravity is rounding it out on the outside. So gravity is acting on the outer surface of the spherical star. So gravity is making it roundish, right? And it's also pushing inward. So we have light pushing out, gravity pushing inward. And when that's in a balanced push-pull stage, it's like a tie in a tug of war, right? Nobody's winning that tug of war. What we call that is the hydrostatic equilibrium state. It's a balanced state. So we say static, meaning it's not accelerating. It's not like changing dynamically, right? So static refers to that state. And the radiation pressure is balanced via the nuclear fusion, the pressure created from nuclear fusion. Okay. So one thing to note is that all the things that govern all the motions of our universe come down to these four fundamental forces. Now, we've talked about gravity. So gravitational force is a fundamental force. It's the weakest force. It doesn't seem so weak in astronomy because we're dealing with really high massive objects. We're not just talking about the mass of a baseball here. We're talking about, you know, the mass of like billions of baseballs combined together. We also have something called the weak nuclear force, which has to do with decay processes. We don't need to get into that. The electromagnetic force comes in a lot too, because it's the positive and negative charges that combine together. It's the force behind electricity and magnetism. And then the strong nuclear force is what's responsible for the fusion process. So sometimes you could have so much of the atoms squeezed together that the protons are forced to combine together. Because typically a proton and a proton are a positive and a positive charge, and they want to repel. But since the strong nuclear force is much stronger than the electromagnetic force, it'll overcome the repulsion of that force, and you'll crush those positives together in a small space. So these terms come up, and it's good to have a good idea how how they play a role in stellar evolution. Okay, so we talked about nuclear fusion before, but again, it's the process of combining two or more atomic nuclei to form one or more different atomic nuclei. Okay, so conservation of mass and energy play a big role, significant role in this process. So what we're doing is we're creating new elements, and the only way fusion is possible is to have high enough temperature. So you have to have a lot of mass to squeeze that mass together. When you're creating that pressure climate, that pressure thermostat is a typical term that's used. What you're doing is you're increasing the temperature to a significant amount such that the fusion process can occur. So you need at least 10 million degrees to do this. I know that they have a project called ITER, ITER, which is trying to create the nuclear fusion process that a star undergoes here in a laboratory, so here on Earth. So anyways, they are trying to replicate this fusion process from a star here, and that's a really, that takes a lot of energy to do. So it's a significant project that's going on, very elaborate. So anyways, you need this high temperature to be able to do that in the core of a star, to fuse this nuclei together. And the high temperatures, again, generated by the mass. So the two main cycles that occur that we're interested in, there's a lot more going on as far as the details, but we just are doing an overview and just kind of want to distinguish between the different types of stars and their evolutions. We have the proton-proton chain, and it's a few different reactions that result in the helium structure and the energy that's emitted from a main sequence star like our sun. So it starts with, and this is done in your book, but it starts with like hydrogen atoms combining to fuse to form a certain nuclei. And then we're doing another fusion reaction to create a helium nuclei. And then the resulting helium-4 nuclei is from the third process of fusion that goes on. So these little arrows right here on the side, these refer to the energy and other subatomic particles that result. Because the mass of this hydrogen atom and this hydrogen atom that fuse together to form this first stage of a hydrogen atom, these are not going to be, and then a helium atom, but these masses are not going to be the same. So all this extra stuff right here add up so that conservation of energy and mass are not violated in the process. Okay, so this is a typical hydrogen to this resulting helium is a typical process for main sequence stars like our sun. Now, if you start with a bigger glob of molecular gas to start your star, so you're starting out with a higher mass star, what happens is you have increased pressure in the core, increased temperatures, such that you could start fusing, do this CNO cycle, which is a fusion of carbon, nitrogen, and oxygen. Okay, so this is typical of a high mass star. Now, if you wanted to get more information, here's a website that I have a link to in the slideshow, and it has a few other key details. So I'm trying to go right through the CNO cycle. So it goes through some more of the steps of the CNO cycle, the 6, all the reactions that occur. That's a little much for this class, so you're not responsible for knowing all 6 of those reactions, but just understand what the CNO cycle means. And then you could go through that and then explore that some more. But what happens with a typical high mass star is you start fusing heavier elements down the periodic table. So we go hydrogen, helium, and then down the road you get to the heavier elements. And we'll see up until iron, which is the last type of possible core for a star. And then beyond that, you need energy to do fusion. So it's a very, you could only fuse atoms up to iron. Okay. So here's our little outline. We looked at this yesterday to kind of give you an overview of what we're going to talk about today, and then fill in some of the details. So here is a typical lifetime of a star like our sun. So we have, oops. My arrows are not working.
You muted yourself, I think.
There we go. All right, so I clicked a bad button there, the mute button. Okay, so here we are. So protostar to T-star from the cold gas, nuclear fusion, most of our lifetime, running out of fuel is the next stage. So this is when we're going to run into, not just that, the running out of fuel stage is when we turn into a red giant. So I have a little plot that you could follow on that. We start bloating when we run out of that fuel, and then we start our dying phase. And eventually we die and become a white dwarf. Okay. So that's really the process of evolution for a star. So the main items to be aware of is where we're actually born. We're always looking for a star birth area. So we talked about that yesterday. So we have 3 types of nebula: emission based on the excitation, the heated up gases; reflection, scattered light; and then we have dark or diffuse nebula, the absorption nebula. Your book has some really good details on that. Make sure you do know those. And just be aware, there's some really awesome nebula. Like you could do a whole slideshow just on nebula. There's like butterfly nebula, there's the owl nebula. These are fun things to look at during a star party. So if you ever get to a star party, when they start gathering beyond the virtual environment, you know, ask one of those astronomers to show you one of the nebula out in the night sky. There's some fascinating ones out there, a lot of good ones to explore. But we like to look at these, and they hold clues on star formation. And a lot of these are remnants from other stars that have deteriorated or have went supernova. So nebula are remnants from other stars, but also areas where we have star formation. Okay, so we talked about the pillars of creation here. This is a big star forming region right here. And next up, looking at evolution, filling in all the blanks here on the evolution of stars, one thing we need to consider are star clusters. Okay, star clusters are really good areas that astronomers like to study because they're groups of stars that are very similar in nature. So they help us. They're formed from the same sort of cloud of gas, and they form. They have different masses attributed to the clumps of gas. So we're looking at the variety of masses that we could actually compare these stars and the stellar evolution with. So when we talk about star clusters, we're just talking about groups of stars that are gravitationally bound, not so much like our galaxy. Our galaxy is a large group of stars, right, that are combined gravitationally into one system. So a star cluster is just a mini group within our galaxy. So we got groups of stars that are gravitationally bound. And open, we have 2 types. We have open clusters, and these are just a few hundred members, and they contain a lot of young hot stars, and they're formed from the same molecular cloud. And this is why we like to study them. We look at them, we look at a star and we look at their siblings, so to speak, and compare their evolution. Okay. So individual stars can be actually resolved, so we can actually see the individual stars are not densely packed together. And then we have globular clusters. These are all the dinosaur stars. They're densely populated clusters. It's like if you, you know, travel towards the center of a city, you'll see like the pack of lights all packed together. Well, towards the center of a galaxy, we have globular clusters. We have a halo of stars all clumped together, and those are the older stars of our galaxies, the first ones that formed. Okay, and what happened is a lot of the star making material has been used up, and there are these just globs of stars, the older type stars like the M stars, the red and yellow type stars. We call these population 2 stars. And so they're located in our galactic halo, which we'll learn a little bit about in our next chapters. And there's no new star formation. So a good site to visit too on star clusters here. So here we have open clusters. That's the Pleiades. The Pleiades are in here. This is a jewel box cluster. It gives you a view on a different type. And then we have so many different types of globular clusters here. Okay. So I have that link in there and you can explore more information on here. Here's M5. I actually have a photo of the same galaxy. I'm going to reduce the size for a minute and show you a picture. This was taken, this is M4. This is another open cluster. This was taken by one of our local astronomers here on the Central Coast. Okay, so you can see that's another object of interest. It's a M object, a Messier object. So it's one of these items of interest for astronomers to try to point their telescopes to. Now, one other thing here, I have this in my notes. So when I post this, you'll be able to see this because I mentioned population 2 stars and globular clusters. Population 1 stars are young metal-rich stars that are formed via the recycled materials from previous stars many times. Okay, so population 1 stars are the youngest type of stars. Population 2 stars are metal-poor stars. So they haven't recycled as much, you know, they've only recycled material from other stars a few times. Now there's another population 3 star. Population 3 stars, they're the very first stars that formed out of the first gases, the primordial gas left over from the Big Bang, the very, very first stars that were born. So we're still trying to find these. There's a race for astronomers to try to find one of these, but they're hard to find because they've dimmed since then. They're hydrogen and helium stars, and they're left over from the Big Bang. So they haven't recycled any from previous stars because they are the first stars. So this is something to try to watch for in the world of astronomy in the future to see if we actually find those. So globular clusters contain these population 2, and open clusters will contain more of the young population 1 stars. Okay, so going back here, what we have is our general outline. So I showed you this last class, and this is really, and I even have a poster here in my room too on stellar evolution. The big thing is to know the difference between low mass stars, medium mass stars, and high mass stars. Okay. Now, also when you're, and I have this on, I'll see if I can try to put this handout up online because I use this. I always give out a lot of handouts for this part of the class. But if you're below 0.08 masses of the sun, which I have on the worksheet, then you're on this brown dwarf category and you fizzle, right? You can't fuse hydrogen into helium. You could only do something called deuterium. So you don't have the regular fusion process. You just slowly dim. So that's a very low mass star here on the bottom. But a low mass star is considered a red dwarf, the most common type of star. And you just burn your fuel for hundreds of billions of years and you slowly dim to what's called a white dwarf. Okay, so white dwarfs are, I think we mentioned it last class, but just to go through. Yeah, they're in the lower left of the HR diagram. So they're no longer fusing, so they have no energy source, and it's just thermal heat. I'm trying to think. You could think of them as dead embers, cores of stars. I do have a better description for them. One second. I guess I don't have. Okay, yeah, that's what I was looking for. So the things to consider for the white dwarfs is the fact that, you were burning all this hydrogen. You're going through the hydrogen into helium fuel. And what happens when you're a small star, you're able to mix your hydrogen many, many more times over. You're continually mixing this fuel. So that's why you're able to, via convection, that's why you're able to last so long. Okay. And then you slowly burn out the fuel. And what happens is you're left with this like dying ember of a core called a white dwarf. A very, very dense core. And it's what we call this degenerate matter, and it's held up by something called electron pressure. And your book goes into that in detail. But a white dwarf really has the electrons pushing up against gravity, which holds it together, and it just slowly cools down. Okay, so low mass stars end up being white dwarfs, but so do medium mass stars. They just go through a different process. So a star like the sun, it doesn't mix up the hydrogen as well. So eventually when you run out of hydrogen fuel, you start burning these things called helium shells. You do the shell burning and you start bloating up to the red giant phase. So you move up to the top right of the HR diagram, okay, off to the right. And then what happens is after you finish blowing, you could basically start expelling that atmosphere that's created via that light pressure. So you start expelling that atmosphere, and that expelled atmosphere is called a planetary nebula. Now, planetary nebula is, we talked about reflection, emission, and dark absorption nebula. A planetary nebula can have a little bit of all those, but it's a little different in the way it's formed. The planetary nebula is just the expelled atmosphere of a dying main sequence star. So what happens is it starts expelling this atmosphere, and then in the center of that planetary nebula is left a white dwarf, a very dense, degenerate core, which eventually cools down and just diminishes. Okay, so white dwarf is what's left in the center there, very dense core. And then a high mass star, which are ones on the upper top left of the HR diagram, blue supergiants, they burn through their fuel. They're squeezed together so much that they burn through their fuel so quickly, they get to what's called an iron core. Once you get to that iron core, you cannot fuse anymore. It takes energy to do that. So it just results in this nuclear chain reaction where it just collapses, it pushes inward so much, and then you get this outward response, right? This explosion. So you have this implosion that occurs that results in this huge explosion, which we call a supernova. That's what we mean by supernova, an exploding star. And we'll see there's different types. So a large high mass star will result in a supernova, and the remnants are what's created in the process of the supernova are heavier elements to that process. And the result, what's left of the core on the inside, is either going to be a neutron star. And again, there's different types of neutron stars like pulsars or magnetars. Or if it's really dense enough, really there's a lot of mass left crunched down to a small radius, then it'll become a black hole, a stellar black hole. Okay, so let's go visit a few more things here. Okay, so here's a little bit more on the sun-like star evolution that we talked about. Okay, here's our red giant stage when we go from main sequence. So it starts fusing helium to carbon, nitrogen, oxygen, and eventually loses all that. And then you can see how it's going to move to this red giant strip, and then it expels its atmosphere, planetary nebula, and then moves down to this white dwarf stage. Oops. Okay, and this is what a planetary nebula looks like, and there's a lot of good ones out there. This is called the Ring Nebula. It's a famous planetary nebula, which is also an emission nebula because we have excited gases here. Okay, so it's emitting. It has spectral lines in the emission spectrum. What we have is, okay, so this takes tens of thousands of years, and eventually the stellar winds carry off all these gases, right, and it diminishes. So what we have here in the center is a white dwarf. So when you look at planetary nebula, always try to see if you can see that white dwarf in the center there. Okay, and what we'll see is sometimes you'll think the white dwarf is, you know, the absolute end game for a star, but sometimes white dwarfs can be revived. And we'll talk about that with this type 1 supernovas. There is a way that white dwarfs could actually steal material from another star in a binary system and then gets reignited. Okay, so and can get revived, so to speak, and that typically ends up in an explosion as well. So anyway, so white dwarfs can come back to life as well, but they typically just cool down in the center of these planetary nebula. Okay, so here is a famous white dwarf. We talked about the system Sirius A and B. It's a binary system. And again, remember, binary systems give us information on the masses of stars through the orbital mechanics. So here we have the white dwarf companion to Sirius A. So again, let's think about how we're going to die. If we're a large mass star, we're going to go supernova, and we're going to end up being a neutron star or a stellar black hole. If we're a medium mass star, we're going to either be a red giant or white dwarf. Red giant to white dwarf, we end up as a white dwarf. And a small mass, we end up as a white dwarf. Now, there's something called the Chandrasekhar limit that tells you at the final stages of evolution for a star, how much mass you have at that stage in comparison to solar masses, because we always compare it to the sun's mass, will tell you what your ultimate ending will be. Chandrasekhar was a famous scientist that did a lot of work on relativity and coming up with these models of mass and what masses would produce a certain ending. Okay, so the Chandrasekhar limits, again, it's determined by the amount of mass left as its fuels run out. So if you're less than 1.4 solar masses, I have mass of the sun here, but sometimes you'll see a little circle with a dot in the middle, and that means in reference to the sun's mass, a solar mass, okay? And if it's less than that, then you're gonna end up being a white dwarf. So if you're between 1.4 and 3 solar masses, your star death will end up as a neutron star. Okay, the electrons and protons combine to form a ball of neutrons. That's what we mean by a neutron star. It's a star just full of neutrons, and it's still held up via gravity through that pressure from the neutrons. And then if the neutron star, you know, starts spinning rapidly, then it's a pulsar. Or a neutron star that's highly magnetic is called a magnetar. We just found these in the 90s because these types of stars their magnetism was so strong that even though that they were light years away, they were able to damage some of the military satellites in orbit around the Earth. So if you know a little bit about magnetism, you know that you should never put a magnet near your cell phone, your computer, anything that's electronic, because what it does is realign the electrons. Okay, so a huge magnet near a satellite is going to be bad, and that's what a magnetar does. The strongest magnetic fields known to us. So they're my favorite stars out there, so you can look them up. They're very interesting. So they're a type of neutron star that have a huge magnetic field. Now this part between number 2, this is sort of hazy. It really depends on the kind of star. And this region is sort of, some people don't even include that. They just say 1.4 to 3 solar masses is either a neutron star or a stellar black hole. But the upper limit here, the star death typically results in the collapse of the core, that it leads to what we call a stellar black hole. So you have to note that there's different kinds of black holes, but a stellar black hole is the collapsed remnant of a star that the gravity is so great that not even light can escape the surface of this core remnant of a star. So more on that in a future slide. Okay, so first we'll talk about supernova, supernovae. So we don't say supernovas, we say supernovae, plural. And there's several types, and they're still being cataloged based on the early 1940s models. So we really have 2 types. Type 1 are, there's no visible hydrogen emission lines, okay? And you have 3 main subgroups, 1A, 1B, and 1C. B and C are core collapse types, but 1A are of particular interest because they're the explosion of the carbon-oxygen white dwarf in a binary star system. And it's due to gaining material through the accretion disk or through a merger, which is the combining of 2 stars together. So what happens is, if you have a white dwarf, here's a 1A, if you have a white dwarf that actually steals material from another star, the surface of the star through the disk around the star, then it could actually take this material and create an explosion called a type 1A supernova. Here's the oldest documented supernova, 185 AD. And this was a white dwarf revived by a companion star. So it's really interesting that we have documents of these way back. So here's the remnants of the supernova. Okay. Type 2 are the result of high mass star explosions, right? And they result from, these have visible hydrogen emission line, and this is the main way that we distinguish between these 2 types. And they result from the iron core collapse of massive stars. Okay, so massive stars, you know, they push inward, and then there's a huge outward reaction push explosion, which creates a supernova. So there was there's several of these. Like here's one that was documented in 1054 AD, and this is the Crab Nebula. These are the remnants, the leftover stuff from that supernova, the metals and all the rest of the stuff from the explosion. And these are found in star-forming regions. So the interesting thing with the type 2 supernova is these are the remnants, the ejected material that's rich with heavy elements. So when people say, when they say we are all made of stardust, if you wanted a correction to that, you could say, well, we are all made out of type 2 supernova remnants because the type 2 remnants, the metal rich, the heavy elements produced from these explosions are the materials that seed the cosmos with the heavy elements, the stuff that we found on Earth, which are rare. Okay, so we're really made out of type 2 supernova remnants. So I'm going to, I have this on the bottom here, my notes. Okay. Oh yeah, here I just have a note on nova. It must be the next slide, but nova are also referred to as explosions, but these are really flare-ups that involve a white dwarf companion due to the mass transfer. So it's not like the end game supernova. They're just mini explosions that occur. But going on to the next disk here, our slide. Okay. So here's another famous supernova. This one's in your book. This is 1987A in the Large Magellanic Cloud, which is a something of interest for people to look at. We're still studying this. It looks like it's being energized a little bit. We can see the gases lighting up. So there's energy being produced somewhere there that's of a curious nature for astronomers who are trying to study what's going on there. But anyways, this happened in 1987, and we were able to see this like actually get brighten up and go supernova, and looking at how the explosion is spreading over time. We are thinking this is going to happen with Betelgeuse soon too. So hopefully that will be something that we could see in our lifetime. It's really interesting. And here's some just some good little figures on trying to understand a little bit between the two differences of the supernova. Here's type 1 with the binary star system. Here's that white dwarf stealing material from the accretion disk and resulting in a detonation. Okay, and then here you have your type 2, the iron core, and then the shock waves that are produced that go outward and produce the explosion. And this is where I have the terms of we are made out of type 2 supernova. And the process on the outward explosion of type 2 is called nuclear synthesis. And that's really responsible for creating all the elements that we see today. Okay, so moving on to the last part here. And we could spend a long time on black holes. I'll post some extra supplements I have on black holes. The one thing I didn't put up on this slide are the Schwarzschild radius, but I'll put some fun computations on the Schwarzschild radius. It's a really fun formula to play around with, and it deals with black holes. So the end-mode for some high mass stars, so if you're in that 2 to 3 solar mass range at the very end of your life, you could very well end up being a stellar mass black hole. And what we mean by a black hole is an object that is so dense, there's so much mass packed in a small radius that gravity is acting on it so strongly that not even light can escape. What we mean by light could be a radio signal or a flashlight. So if you're in a black hole, so supposing you could survive that in some out of normal everyday physics, so to speak, science, if you're able to shine a flashlight in that black hole, nobody would see that light coming out of that black hole. Okay, nobody would hear your radio signal or your Wi-Fi signal coming out of that black hole. So all we don't really see the black hole. What we see is the matter, the accretion disks around black hole. We take images of the material and the energy and the light surrounding that black hole. Now, the tidal effects, what we mean by tidal effects are the force of gravity, are so great around these objects. So these tidal forces are these push or pulls are so strong. So if you're at very close to the black hole, if you're at a certain radius close to the black hole, and you compare that gravity to a little further out from that black hole, let's say 10 times further away, the gravity differences are extreme. So you'll get pulled so much more here in the front than you will in the back that you get this process called spaghettification that will occur, right? And that's when you this extreme elongation or stretching of an object, okay? And we have a lot of other effects that come into play, relativistic effects like time dilation. If you had a spaceship really close to the black hole here and you had another one a little further away, what you're going to notice is that your clocks will differ by a lot. The spaceship further out from the black hole maybe will record like 5 hours passing, but the spaceship closer to the black hole might only record 1 hour passing. Okay, the closer you are to that, the gravity bends the space around it so much more because it's such a strong gravity field that it will create differences in time. That's called time dilation. Now, the boundary line around a black hole for which you can no longer see the light is called the event horizon. And of course, that's the name of our big telescope out there, the Event Horizon Telescope. So we have a telescope just dedicated to looking at black holes, and I'll post that up on our site. I'm just making a note of that because I did forget to add that in here. And the event horizon is the point of no return. So there is a formula called the Schwarzschild radius, which you could find the event horizon for any mass object. Like you could figure out what radius you would need to shrink the Earth to make the Earth into a black hole. So you could potentially create a black hole of the Earth. You just have to squeeze everything together, and then you would have a radius for that, which would be the event horizon. Okay, so here's the question: what radius would the Earth turn into to make a black hole? Okay, so we'll check that out here in a second. Black holes have accretion disks around them, so we have high energy emissions, X-rays here, and that's how we know they're there. And one thing to note is we'll look at supermassive black holes, which are different than stellar black holes. Supermassive black holes are the black holes in the center of our galaxies. And there's a few other types of black holes out there, but they're the main ones that we refer to in astronomy. So let's see if we can see the black hole calculator here. And we'll look at it in meters. Okay. I'm not really sure why I don't have a value coming up here. All right, but I'll play around with that. I'll send you the figures on that. This should be. Okay, I'll come back to that and play around with that. But there's a way to find that out, and I'll show you the formula which you could do yourself for that. And I have a table of figures. I might add that into this slide that I use in class. And just one last bit here. All right, so just some effects around black holes, relativistic effects. I have some information on time dilation. There's something called the twin paradox you could look at that refers to time dilation, which is something that comes out of relativity theory, special relativity. General relativity is like the theory of gravity as well. So we have time dilation effects are one of the big ones. We get large accelerations and a high curvature of the space. So we're talking about really warped space around black holes. And then we have these extreme tidal forces, differences in gravitational pulls. And then we have the accretion disks of high energy emissions around them.